Lisp programming language. Historically, Lisp is a family of programming languages with a long history and a distinctive, fully parenthesized prefix notation. Originally specified in 1958, Lisp is the second oldest high-level programming language still in common use. Only Fortran is older by 1 year. Lisp has changed since its early days, and many dialects have existed over its history. Today, the best-known general-purpose Lisp dialects are Racket, Common Lisp Scheme, and Clojure. Lisp was originally created as a practical mathematical notation for computer programs, influenced by, though not originally derived, from the notation of Alonzo Church's Lambda calculus. It quickly became the favored programming language for artificial intelligence AI research. As one of the earliest programming languages, Lisp pioneered many ideas in computer science, including tree data structures, automatic storage management, dynamic typing, conditionals, higher-order functions, recursion, the self-hosting compiler, and the read-eval-print loop. The name Lisp derives from Lisp processor. Linked lists are one of Lisp's major data structures, and Lisp source code is made of lists. Thus, Lisp programs can manipulate source code as a data structure, giving rise to the macro systems that allow programmers to create new syntax or new domain-specific languages embedded in Lisp. The interchangeability of code and data gives Lisp its instantly recognizable syntax. All program code is written as expressions or parenthesized lists. A function call or syntactic form is written as a list with the function or operator's name first and the arguments following. For instance, a function f that takes 3 arguments would be called as f argon arg2 arg3. History. John McCarthy developed Lisp in 1958 while he was at the Massachusetts Institute of Technology, MIT. McCarthy published its design in a paper in Communications of the ACM in 1960 entitled Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part I. He showed that with a few simple operators and a notation for anonymous functions borrowed from Church, one can build a Turing-complete language for algorithms. Information processing language was the first AI language from 1955 or 1956, and already included many of the concepts, such as list processing and recursion, which came to be used in Lisp. McCarthy's original notation used bracketed M expressions that would be translated into S expressions. As an example, the M expression car cons A B is equivalent to the S expression car cons A B. Once Lisp was implemented, programmers rapidly chose to use S expressions, and M expressions were abandoned. M expressions surfaced again with short-lived attempts of M-Lisp by Horace Ennia and Seagull by Vaughan Pratt. Lisp was first implemented by Steve Russell on an IBM 704 computer using punched cards. Russell had read McCarthy's paper and realized to McCarthy's surprise that the Lisp eval function could be implemented in machine code. According to McCarthy, Steve Russell said, "Look, why don't I program this eval?" And I said to him, "Ho ho, you're confusing theory with practice. This eval is intended for reading, not for computing." But he went ahead and did it. That is, he compiled the eval in my paper into IBM 704 machine code, fixing bugs, and then advertised this as a Lisp interpreter, which it certainly was. So at that point Lisp had essentially the form that it has today. Today. The result was a working Lisp interpreter which could be used to run Lisp programs or, more properly, evaluate Lisp expressions. 2 assembly language macros for the IBM 704 became the primitive operations for decomposing lists: car contents of the address part of register number and CDR contents of the decrement part of register number, where register refers to registers of the computer's central processing unit CPU. Lisp dialects still use char and cdr and for the operations that return the first item in a list and the rest of the list, respectively. The first complete Lisp compiler, written in Lisp, was implemented in 1962 by Tim Hart and Mike Levin at MIT, and could be compiled by simply having an existing Lisp interpreter interpret the compiler code, producing machine code output able to be executed at a 40-fold improvement in speed over that of the interpreter. This compiler introduced the Lisp model of incremental compilation, in which compiled and interpreted functions can intermix freely. The language used in Hart and Levin's memo is much closer to modern Lisp style than McCarthy's earlier code. Garbage collection routines were developed by MIT graduate student Daniel Edwards prior to 1962. During the 1980s and 1990s, a great effort was made to unify the work on new Lisp dialects, mostly successors to MacLisp such as Zeta-Lisp and NIL new implementation of Lisp into a single language. The new language, Common Lisp, was somewhat compatible with the dialects it replaced. The book Common Lisp, the language, notes the compatibility of various constructs. In 1994, ANSI published the Common Lisp standard, ANSI X 3.226-1994 Information Technology Programming Language Common Lisp. Timeline. Connection to artificial intelligence. Since inception, Lisp was closely connected with the artificial intelligence research community, especially on PD-10 systems. Lisp was used as the implementation of the language microplanner, which was used in the famous AA system SHRDLU. In the 1970s, as AI research spawned commercial offshoots, the performance of existing Lisp systems became a growing issue. Genealogy and variants. Over its 60-year history, Lisp has spawned many variations on the core theme of an S-expression language. Moreover, each given dialect may have several implementations. For instance, there are more than a dozen implementations of Common Lisp. Differences between dialects may be quite visible. For instance, Common Lisp uses the keyword defun to name a function, but Scheme uses define. Within a dialect that is standardized, however, conforming implementations support the same core language, but with different extensions and libraries. Historically significant dialects. Lisp 1 first implementation. Lisp 1.5 first widely distributed version, developed by McCarthy and others at MIT. So named because it contained several improvements on the original Lisp 1 interpreter, but was not a major restructuring as the planned Lisp 2 would be. Stanford Lisp 1.6. This was a successor to Lisp 1.5 developed at the Stanford AI Lab and widely distributed to PD-10 systems running the TOP-10 operating system. It was rendered obsolete by MacLisp and InterLisp. MacLisp developed for MIT Project MACI. MacLisp is a direct descendant of Lisp 1.5. It ran on the PD-10 and Multics systems. MacLisp would later come to be called MacLisp and is often referred to as MacLisp. The MACI in MacLisp is related neither to Apple's Macintosh nor to McCarthy. InterLisp, developed at BBN Technologies for PD-10 systems running the 10X operating system, later adopted as a West Coast Lisp for the Xerox Lisp machines as InterLisp-D. A small version called InterLisp 65 was published for the 6502-based Atari 8-bit family computer line. For quite some time, MacLisp and InterLisp were strong competitors. France Lisp, originally a University of California, Berkeley project, later developed by France Inc. The name is a humorous deformation of the name France Lisp and does not refer to Allegro Common Lisp, the dialect of Common Lisp sold by France Inc. X-Lisp, which Auto Lisp was based on. Standard Lisp and Portable Standard Lisp were widely used and ported, especially with the computer algebra system Reduce. Zeta-Lisp, also termed Lisp Machine Lisp, used on the Lisp machines, direct descendant of MacLisp. Zeta-Lisp had a big influence on Common Lisp. The Lisp is a French Lisp dialect. One of the first interface builders, called SOS Interface, was written in Lisp. Scheme 1975. Common Lisp 1984, as described by Common Lisp the language, a consolidation of several divergent attempts, Zeta Lisps, Pice Lisp Nil, and Sminus1 Lisp to create successor dialects to MacLisp, with substantive influences from the Scheme dialect as well. This version of Common Lisp was available for wide-ranging platforms and was accepted by many as a de facto standard until the publication of ANSI Common Lisp ANSI X 3.226-1994. Among the most widespread subdialects of Common Lisp are Steel Bank Common Lisp SPCL, CMU Common Lisp CMU-CL, Clojure OpenMCL, not to be confused with Clojure, GNU-C-Lisp, and later versions of France Lisp. All of them adhere to the later ANSI CL standard, see below. Dylan was in its first version a mix of Scheme with the Common Lisp object system. EU-Lisp attempt to develop a new efficient and cleaned up Lisp. IS-Lisp attempt to develop a new efficient and cleaned up Lisp. Standardized as ISO/IEC 13816 1997 and later revised as ISO/IEC 13816 2007. Information technology, programming languages, their environments, and system software interfaces. Programming language IS-Lisp. E-Scheme Standard 1178 1990 R 1995. ANSI Common Lisp and American National Standards Institute ANSI Standard for Common Lisp, created by Subcommittee X3J13, chartered to begin with Common Lisp, the language as a base document, and to work through a public consensus process to find solutions to shared issues of portability of programs and compatibility of Common Lisp implementations. Although formally an ANSI standard, the implementation, sale, use, and influence of ANSI Common Lisp has been and continues to be seen worldwide. ACL2, or a computational logic for applicative Common Lisp, an applicative side effect-free variant of Common Lisp. ACL2 is both a programming language which can model computer systems and a tool to help proving properties of those models. Clojure, a recent dialect of Lisp which compiles to the Java virtual machine and has a particular focus on concurrency. Game-oriented assembly Lisp, or GOL, is a video game programming language developed by Andy Gavin and the Jack and Daxter team at Naughty Dog. It was written using Allegro Common Lisp and used in the development of the entire Jack and Daxter series of games. Chi-Lisp, a high-level dialect compiling down to CLVM, the on-chain programming environment in Chia blockchain. 2000 to present. After having declined somewhat in the 1990s, Lisp has experienced a resurgence of interest after 2000. Most new activity has been focused around implementations of Common Lisp, Scheme, Emacs Lisp, Clojure, and Racket, and includes development of new portable libraries and applications. Many new Lisp programmers were inspired by writers such as Paul Graham and Eric S. Raymond to pursue a language others considered antiquated. New Lisp programmers often describe the language as an eye-opening experience and claim to be substantially more productive than in other languages. This increase in awareness may be contrasted to the AI winter and Lisp's brief gain in the mid-1990s. As of 2010, there were 11 actively maintained Common Lisp implementations. Pioneer Common Lisp is a new commercial implementation forked from Symbolic with a first release in 2002. The open source community has created new supporting infrastructure. Symbolic is a wiki that collects Common Lisp-related information. The Common Lisp directory lists resources. HashLisp is a popular IRC channel and allows the sharing and commenting of code snippets with support by Lisp-based and IRC bot written in Lisp. Planet Lisp collects the content. Common Lisp Net is a hosting site for open-source Common Lisp projects. QuickLisp is a library manager for Common Lisp. 50 years of Lisp 1958-2008 was celebrated at Elias 50 at Uppsala. There are regular local user meetings in Boston, Vancouver, and Hamburg. Other events include the European Common Lisp Meeting, the European Lisp Symposium, and an international Lisp conference. The Scheme community actively maintains over 20 implementations. Several significant new implementations Chicken, Gambit, Go Shakaris, Larceny, Epsilon have been developed in the 2000s decade. The ReviseFiv report on the algorithmic language scheme standard of Scheme was widely accepted in the Scheme community. The Scheme requests for implementation process has created a lot of quasi-standard libraries and extensions for Scheme. User communities of individual Scheme implementations continue to grow. A new language standardization process was started in 2003 and led to the R6-RS Scheme standard in 2007. Academic use of Scheme for teaching computer science seems to have declined somewhat. Some universities are no longer using Scheme in their computer science introductory courses. MIT now uses Python instead of Scheme for its undergraduate computer science program and MIT's massive open online course. There are several new dialects of Lisp: Arc, High New Liskel, and Elify Lisp flavored Erlang. The parser for Julia is implemented in FemtoLisp, a dialect of Scheme. Julia is inspired by Scheme, which in turn is a Lisp dialect. In October 2019, Paul Graham released a specification for Bell, a new dialect of Lisp. Major dialects. Common Lisp and Scheme represent two major streams of Lisp development. These languages embody significantly different design choices. Common Lisp is a successor to MacLisp. The primary influences were Lisp Machine Lisp, MacLisp, Nil, Sminus1 Lisp, Spice Lisp, and Scheme. It has many of the features of Lisp Machine. Lisp, a large Lisp dialect used to program Lisp machines, but was designed to be efficiently implementable on any personal computer or workstation. Common Lisp is a general-purpose programming language and thus has a large language standard including many built-in data types, functions, macros, and other language elements, and an object system. Common Lisp object system. Common Lisp also borrowed certain features from Scheme such as lexical scoping and lexical closures. Common Lisp implementations are available for targeting different platforms such as the LLVM, the Java Virtual Machine, x86-64, PowerPC Alpha, ARM, Motorola 68000, and MIPS, and operating systems such as Windows, macOS, Linux, Solaris, FreeBSD, NetBSD, OpenBSD, DragonflyBSD, and Heroku. Scheme is a statically scoped and properly tailed recursive dialect of the Lisp programming language invented by Guy L. Steele, Jr. and Gerald J. Sussman. It was designed to have exceptionally clear and simple semantics and few different ways to form expressions. Designed about a decade earlier than Common Lisp, Scheme is a more minimalist design. It has a much smaller set of standard features, but with certain implementation features such as tail call optimization and full continuations not specified in Common Lisp. A wide variety of programming paradigms, including imperative, functional, and message passing styles, find convenient expression in Scheme. Scheme continues to evolve with a series of standards revised in report on the algorithmic language Scheme and a series of Scheme requests for implementation. Clojure is a recent dialect of Lisp that targets mainly the Java Virtual Machine and the Common Language Runtime CLR, the Python VM, the Ruby VM YARV, and compiling to JavaScript. It is designed to be a pragmatic general-purpose language. Clojure draws considerable influences from Haskell and places a very strong emphasis on immutability. Clojure provides access to Java frameworks and libraries with optional type hints and type inference, so that calls to Java can avoid reflection and enable fast primitive operations. Clojure is not designed to be backwards compatible with other Lisp dialects. Further, Lisp dialects are used as scripting languages in many applications, with the best known being Emacs Lisp in the Emacs editor, Auto Lisp and later Visual Lisp in AutoCAD, Nyquist in Audacity, and Scheme in LilyPond. The potential small size of a useful Scheme interpreter makes it particularly popular for embedded scripting. Examples include Syad and Tiny Scheme, both of which have been successfully embedded in the GIMP image processor under the generic name script foo. librep, a Lisp interpreter by John Harper originally based on the Emacs Lisp language, has been embedded in the Sawfish window manager. Standardized dialects. Lisp has officially standardized dialects: R6 RS Scheme, R7 RS Scheme, E Scheme, ANSI Common Lisp, and ISO Lisp. Language innovations. Lisp was the first language where the structure of program code is represented faithfully and directly in a standard data structure, a quality much later dubbed homogeneity. Thus, Lisp functions can be manipulated, altered, or even created within a Lisp program without lower-level manipulations. This is generally considered one of the main advantages of the language with regard to its expressive power, and makes the language suitable for syntactic macros and metacircular evaluation. A conditional using an if-then-else syntax was invented by McCarthy in a Fortran context. He proposed its inclusion in ALGOL, but it was not made part of the ALGOL 58 specification. For Lisp, McCarthy used the more general const structure. ALGOL 60 took up if-then-else and popularized it. Lisp deeply influenced Alan Kay, the leader of the research team that developed Smalltalk at Xerox PARC, and in turn Lisp was influenced by Smalltalk, with later dialects adopting object-oriented programming features, inheritance classes, encapsulating instances, message passing, etc. in the 1970s. The Flavors object system introduced the concept of multiple inheritance and the mixin. The common Lisp object system provides multiple inheritance, multimethods with multiple dispatch, and first-class generic functions, yielding a flexible and powerful form of dynamic dispatch. It has served as the template for many subsequent Lisp, including scheme object systems, which are often implemented via MetaObject protocol, a reflective metacircular design in which the object system is defined in terms of itself. Lisp was only the second language after Smalltalk and is still one of the very few languages to possess such a MetaObject system. Many years later, Alan Kay suggested that as a result of the confluence of these features, only Smalltalk and Lisp could be regarded as properly conceived object-oriented programming systems. Lisp introduced the concept of automatic garbage collection, in which the system walks the heap looking for unused memory. Progress in modern sophisticated garbage collection algorithms, such as generational garbage collection, was stimulated by its use in Lisp. Edgar W. Dijkstra, in his 1972 Turing Award lecture, said, "With a few very basic principles at its foundation, Lisp has shown a remarkable stability. Besides that, Lisp has been the carrier for a considerable number of, in a sense, our most sophisticated computer applications. Lisp has jokingly been described as the most intelligent way to misuse a computer. I think that description a great compliment because of its suitability to complex and dynamic applications. Lisp is enjoying some resurgence of popular interest in the 2010s. Syntax and semantics. Note: this article's examples are written in Common Lisp, though most are also valid in Scheme. Symbolic expressions as expressions. Lisp is an expression-oriented language. Unlike most other languages, no distinction is made between expressions and statements. All code and data are written as expressions. When an expression is evaluated, it produces a value in Common Lisp, possibly multiple values, which can then be embedded into other expressions. Each value can be any data type. McCarthy's 1958 paper introduced two types of syntax: symbolic expressions as expressions, SEX, which mirror the internal representation of code and data, and meta-expressions, expressions, which express functions of as expressions. Expressions never found favor, and almost all lists today use as expressions to manipulate both code and data. The use of parentheses is Lisp's most immediately obvious difference from other programming language families. As a result, students have long given Lisp nicknames such as Lost in Stupid Parentheses or lots of irritating superfluous parentheses. However, the S expression syntax is also responsible for much of Lisp's power. The syntax is simple and consistent, which facilitates manipulation by computer. However, the syntax of Lisp is not limited to traditional parentheses notation. It can be extended to include alternative notations. For example, XMLisp is a common Lisp extension that employs the MetObject protocol to integrate S expressions with the extensible markup language XML. The reliance on expressions gives the language great flexibility. Because Lisp functions are written as lists, they can be processed exactly like data. This allows easy writing of programs which manipulate other programs' metaprogramming. Many Lisp dialects exploit this feature using macro systems, which enables extension of the language almost without limit. Lists. A Lisp list is written with its elements separated by white space and surrounded by parentheses. For example, 1, 2, foo is a list whose elements are the three atoms 1, 2, and foo. These values are implicitly typed. They are respectively two integers and a Lisp-specific data type called a symbol, and do not have to be declared as such. The empty list is also represented as the special atom nil. This is the only entity in Lisp which is both an atom and a list. Expressions are written as lists using prefix notation. The first element in the list is the name of a function, the name of a macro, a Lambda expression, or the name of a special operator. See below. The remainder of the list are the arguments. For example, the function list returns its arguments as a list, so the expression evaluates to the list 1, 2, foo. The quote before the foo in the preceding example is a special operator which returns its argument without evaluating it. Any unquoted expressions are recursively evaluated before the enclosing expression is evaluated. For example, evaluates to the list 1, 2, 3, 4. Note that the third argument is a list. Lists can be nested. Operators. Arithmetic operators are treated similarly. The expression evaluates to 10. The equivalent under infix notation would be 1 plus 2 plus 3 plus 4. Lisp has no notion of operators as implemented in algol-derived languages. Arithmetic operators in Lisp are variadic functions or an array able to take any number of arguments. A C-style ++ increment operator is sometimes implemented under the name inc, giving syntax equivalent to set x plus x1, returning the new value of x. Special operators, sometimes called special forms, provide Lisp's control structure. For example, the special operator if takes 3 arguments. If the first argument is non-nil, it evaluates to the second argument, otherwise it evaluates to the third argument. Thus, the expression evaluates to 3, 4 bar. Of course, this would be more useful if a non-trivial expression had been substituted in place of nil. Lisp also provides logical operators and or and not. The and or operators do short-circuit evaluation and will return their first nil and non-nil argument respectively. We'll evaluate to James. Lambda expressions and function definition. Another special operator, lambda, is used to bind variables to values which are then evaluated within an expression. This operator is also used to create functions. The arguments to lambda are a list of arguments, and the expression or expressions to which the function evaluates the returned value is the value of the last expression that is evaluated. The expression evaluates to a function that, when applied, takes one argument, binds it to arg, and returns the number 1 greater than that argument. Lambda expressions are treated no differently from named functions. They are invoked the same way. Therefore, the expression evaluates to 6. Here we're doing a function application. We execute the anonymous function by passing to it the value 5. Named functions are created by storing a lambda expression in a symbol using the defun macro. Defun f of b defines a new function named f in the global environment. It is conceptually similar to the expression, where set is a macro used to set the value of the first argument f definition, F to a new function object. F definition is a global function definition for the function named F. Hash is an abbreviation for function special operator, returning a function object. Atoms. In the original Lisp, there were two fundamental data types, atoms and lists. A list was a finite ordered sequence of elements, where each element is either an atom or a list, and an atom was a number or a symbol. A symbol was essentially a unique named item, written as an alphanumeric string in source code, and used either as a variable name or as a data item in symbolic processing. For example, the list FOBAR 1, 2 contains 3 elements, the symbol FOO, the list BAR1, and the number 2. The essential difference between atoms and lists was that atoms were immutable and unique. Two atoms that appeared in different places in source code but were written in exactly the same way represented the same object, whereas each list was a separate object that could be altered independently of other lists and could be distinguished from other lists by comparison operators. As more data types were introduced in later Lisp dialects and programming styles evolved, the concept of an atom lost importance. Many dialects still retained the predicate atom for legacy compatibility, defining it true for any object which is not a cons. Consays and lists. A Lisp list is implemented as a singly linked list. Each cell of this list is called a cons in scheme. A parent is composed of two pointers, called the car and CDR. These are respectively equivalent to the data and next fields discussed in the article Linked List. Of the many data structures that can be built out of cons cells, one of the most basic is called a proper list. A proper list is either the special nil empty list symbol, or a cons in which the car points to a datum which may be another cons structure, such as a list, and the CDR points to another proper list. If a given cons is taken to be the head of a linked list, then its car points to the first element of the list, and its CDR points to the rest of the list. For this reason, the car and CDR functions are also called first and rest when referring to consays which are part of a linked list rather than, say, a tree. Thus, a Lisp list is not an atomic object, as an instance of a container class in C++ or Java would be. A list is nothing more than an aggregate of linked consays. A variable that refers to a given list is simply a pointer to the first cons in the list. Traversal of a list can be done by cdring down the list, that is, taking successive CDRs to visit each cons of the list, or by using any of several higher-order functions to map a function over a list. Because consays and lists are so universal in list systems, it is a common misconception that they are lists-only data structures. In fact, all but the most simplistic lists have other data structures, such as vectors, arrays, hash tables, structures, and so forth. S expressions represent lists, Zent lists. Parenthesized S expressions represent linked list structures. There are several ways to represent the same list as an S expression. A cons can be written in dotted pair notation as A, B, where A is the car and B the CDR. A longer proper list might be written A, B, C, E, 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 D, nil in dotted pair notation. This is conventionally abbreviated as a BCD in Lisp notation. An improper list may be written in a combination of the two as a BC, D for the list of three consays whose last CDR is DIE, the list A, list A, B, C, D in fully specified form. List processing procedures, procedures. Shared structure. Lisp lists, being simple linked lists, can share structure with one another. That is to say, two lists can have the same tail or final sequence of consays. For instance, after the execution of the following common Lisp code, the lists foo and bar are a BC and XBC respectively. However, the tail BC is the same structure in both lists. It is not a copy. The cons cells pointing to B and C are in the same memory locations for both lists. Sharing structure rather than copying can give a dramatic performance improvement. However, this technique can interact in undesired ways with functions that alter lists passed to them as arguments. Altering one list, such as by replacing the C with a goose, will affect the other. This changes foo to a b goose, but thereby also changes bar to x b goose, a possibly unexpected result. This can be a source of bugs, and functions which alter their arguments are documented as destructive for this very reason. Aficionados of functional programming avoid destructive functions. In the scheme dialect, which favors the functional style, the names of destructive functions are marked with a cautionary exclamation point or bang, such as set car. Read set car bang, which replaces the car of a cons. In the common Lisp dialect, destructive functions are commonplace. The equivalent of set car is named rplaca for replace car. This function is rarely seen, however, as common Lisp includes a special facility set to make it easier to define and use destructive functions. A frequent style in common Lisp is to write code functionally without destructive calls when prototyping, then to add destructive calls as an optimization where it is safe to do so. Self-evaluating forms and quoting. Lisp evaluates expressions which are entered by the user. Symbols and lists evaluate to some other, usually simpler expression. For instance, a symbol evaluates to the value of the variable it names, plus 2, 3 evaluates to 5. However, most other forms evaluate to themselves. If entering 5 into Lisp, it returns 5. Any expression can also be marked to prevent it from being evaluated, as is necessary for symbols and lists. This is the role of the quote special operator, or its abbreviation, one quotation mark. For instance, usually if entering the symbol foo, it returns the value of the corresponding variable. Both common Lisp and Scheme also support the backquote operator termed quasi-quote in Scheme, entered with the character grave accent. This is almost the same as the plain quote, except it allows expressions to be evaluated and their values interpolated into a quoted list with the comma, unquote, and comma at splice operators. If the variable snoo has the value, it may be possible to modify the values of mutable literals in program code. For instance, if a function returns a quoted form and the code that calls the function modifies the form, this may alter the behavior of the function on subsequent invocations. Modifying a quoted form like this is generally considered bad style and is defined by ANSI Common Lisp as erroneous, resulting in undefined behavior in compiled files because the file compiler can colist similar constants, put them in write-protected memory, etc. Lisp's formalization of quotation has been noted by Douglas Hofstadter in Gödel, Escher, Bach, and others as an example of the philosophical idea of self-reference. Scope and closure. The Lisp family splits over the use of dynamic or static aka lexical scope. Clojure, Common Lisp, and Scheme make use of static scoping by default, while New Lisp, PicoLisp, and the embedded languages in Emacs and AutoCAD use dynamic scoping. Since version 24.1, Emacs uses both dynamic and lexical scoping. List structure of program code, exploitation by macros and compilers. A fundamental distinction between Lisp and other languages is that in Lisp, the textual representation of a program is simply a human-readable description of the same internal data structures, linked lists, symbols, number, characters, etc., as would be used by the underlying Lisp system. Lisp uses this to implement a very powerful macro system. Like other macro languages, such as the one defined by the C preprocessor, the macro preprocessor for the C, Objective-C, and C++ programming languages, a macro returns code that can then be compiled. However, unlike C preprocessor macros, the macros are Lisp functions and so can exploit the full power of Lisp. Further, because Lisp code has the same structure as lists, macros can be built with any of the Lisp processing functions in the language. In short, anything that Lisp can do to a data structure, Lisp macros can do to code. In contrast, in most other languages, the parser's output is purely internal to the language implementation and cannot be manipulated by the programmer. This feature makes it easy to develop efficient languages within languages. For example, the common Lisp object system can be implemented cleanly as a language extension using macros. This means that if an application needs a different inheritance mechanism, it can use a different object system. This is in stark contrast to most other languages. For example, Java does not support multiple inheritance, and there is no reasonable way to add it. In simplistic Lisp implementations, this list structure is directly interpreted to run the program. A function is literally a piece of list structure, which is traversed by the interpreter in executing it. However, most substantial Lisp systems also include a compiler. The compiler translates list structure into machine code or bytecode for execution. This code can run as fast as code compiled in conventional languages, such as C. Macros expand before the compilation step and thus offer some interesting options. If a program needs a precomputed table, then a macro might create the table at compile time, so the compiler need only output the table and need not call code to create the table at runtime. Some Lisp implementations even have a mechanism, eval-when, that allows code to be present during compile time when a macro would need it, but not present in the emitted module. Evaluation and the read-eval-print loop. Lisp languages are often used with an interactive command line, which may be combined with an integrated development environment IDE. The user types in expressions at the command line or directs the IDE to transmit them to the Lisp system. Lisp reads the entered expressions, evaluates them, and prints the result. For this reason, the Lisp command line is called a read-eval-print loop REPL. The basic operation of the REPL is as follows. This is a simplistic description which omits many elements of a real list, such as quoting and macros. The read function accepts textual expressions as input and parses them into an internal data structure. For instance, if you type the text +12 at the prompt, read translates this into a linked list with three elements, the symbol plus, the number 1, and the number 2. It so happens that this list is also a valid piece of Lisp code, that is, it can be evaluated. This is because the car of the list names a function the addition operation. Note that a foo will be read as a single symbol. 123 will be read as the number 123. 123 will be read as the string 123. The eval function evaluates the data returning 0 or more other list data as a result. Evaluation does not have to mean interpretation. Some Lisp systems compile every expression to native machine code. It is simple, however, to describe evaluation as interpretation to evaluate a list whose car names a function. Eval first evaluates each of the arguments given in its CDR, then applies the function to the arguments. In this case, the function is addition, and applying it to the argument list 1, 2 yields the answer 3. This is the result of the evaluation. The symbol foo evaluates to the value of the symbol foo. Data like the string 123 evaluates to the same string. The list quote 123 evaluates to the list 123. It is the job of the print function to represent output to the user. For a simple result such as 3, this is trivial. An expression which evaluated to a piece of list structure would require that print traverse the list and print it out as an S expression. To implement a Lisp REPL, it is necessary only to implement these 3 functions and an infinite loop function. Naturally, the implementation of eval will be complex, since it must also implement all special operators like if or lambda. This done, a basic REPL is one line of code, loop print eval read. The Lisp REPL typically also provides input editing, an input history, error handling, and an interface to the debugger. Lisp is usually evaluated eagerly. In common Lisp, arguments are evaluated in applicative order leftmost innermost, while in scheme order of arguments is undefined, leaving room for optimization by a compiler. Control structures. Lisp originally had very few control structures, but many more were added during the language's evolution. Lisp's original conditional operator, cond, is the precursor to later if-then-else structures. Programmers in the Scheme dialect often express loops using tail recursion. Scheme's commonality in academic computer science has led some students to believe that tail recursion is the only or the most common way to write iterations in Lisp, but this is incorrect. All oft-seen Lisp dialects have imperative-style iteration constructs, from Scheme's do loop to common Lisp's complex loop expressions. Moreover, the key issue that makes this an objective rather than subjective matter is that Scheme makes specific requirements for the handling of tail calls, and thus the reason that the use of tail recursion is generally encouraged for Scheme is that the practice is expressly supported by the language definition. By contrast, ANSI Common Lisp does not require the optimization commonly termed a tail call elimination. Thus, the fact that tail recursive style as a casual replacement for the use of more traditional iteration constructs such as do, list, or loop is discouraged in Common Lisp is not just a matter of stylistic preference, but potentially one of efficiency, since an apparent tail call in Common Lisp may not compile as a simple jump, and program correctness, since tail recursion may. Some Lisp control structures are special operators, equivalent to other languages' syntactic keywords. Expressions using these operators have the same surface appearance as function calls, but differ in that the arguments are not necessarily evaluated or, in the case of an iteration expression, may be evaluated more than once. In contrast to most other major programming languages, Lisp allows implementing control structures using the language. Several control structures are implemented as Lisp macros and can even be macro expanded by the programmer who wants to know how they work. Both Common Lisp and Scheme have operators for non-local control flow. The differences in these operators are some of the deepest differences between the two dialects. Scheme supports reentrant continuations using the call/cc procedure, which allows a program to save and later restore a particular place in execution. Common Lisp does not support reentrant continuations, but does support several ways of handling escape continuations. Often, the same algorithm can be expressed in Lisp in either an imperative or a functional style. As noted above, Scheme tends to favor the functional style, using tail recursion and continuations to express control flow. However, imperative style is still quite possible. The style preferred by many Common Lisp programmers may seem more familiar to programmers used to structured languages such as C, while that preferred by schemers more closely resembles pure functional languages such as Haskell. Because of Lisp's early heritage in Lisp processing, it has a wide array of higher-order functions relating to iteration over sequences. In many cases where an explicit loop would be needed in other languages, like a for loop in C, in Lisp the same task can be accomplished with a higher-order function. The same is true of many functional programming languages. A good example is a function which in Scheme is called map, and in Common Lisp is called mapper. Given a function and one or more lists, mapper applies the function successively to the list's elements in order, collecting the results in a new list. This applies the plus function to each corresponding pair of list elements, yielding the result 11, 22, 33, 44, 55. Examples. Here are examples of Common Lisp code. The basic Hello World program. Lisp syntax lends itself naturally to recursion. Mathematical problems such as the enumeration of recursively defined sets are simple to express in this notation. For example, to evaluate a number's factorial, an alternative implementation takes less stack space than the previous version if the underlying Lisp system optimizes tail recursion. Contrast the examples above with an iterative version which uses Common Lisp's loop macro. The following function reverses a list. Lisp's built-in reverse function does the same thing. Object systems. Various object systems and models have been built on top of, alongside, or into Lisp, including the Common Lisp object system, close, is an integral part of ANSI Common Lisp. Close descended from new flavors and common loops. ANSI Common Lisp was the first standardized object-oriented programming language 1994, ANSI X3 J13. Object-Lisp or Object-Lisp used by Lisp machines incorporated an early versions of Macintosh Common Lisp, Loop's Lisp object-oriented programming system, and the later Common Loops flavors built at MIT, and its descendant new flavors developed by Symbolics. CARE, short for knowledge representation, a constraints-based object system developed to aid the writing of Garnet, a GUI library for Common Lisp. Knowledge engineering environment KE used an object system named Units and integrated it with an inference engine and a truth maintenance system Atoms. Operating systems. Several operating systems, including language-based systems, are based on Lisp use Lisp features, conventions, methods, data structures, etc., or are written in Lisp, including Genera, renamed OpenGenera by Symbolics, Medley, written in Interlisp, originally a family of graphical operating systems that ran on Xerox's later Star workstations, Mezzano Interim, Chrysalisp by developers of Tau Systems Taus, and the very Lisp-like Urbit, using Ethereum cryptocurrency technology.